Our topic for this lecture is combined loading. So throughout the semester we've studied various ways that we can load structures. We've talked about tension, direct shear, torsion, bending, transverse shear stresses and beams, and pressure vessel type loading, and we studied each of these things separately. For our subject of combined loading, any or all of these can act on a structure at the same time. So long as our system stays linear, and for us in our class that means long as the material stays linear elastic, the stresses at any one point from each type of loading can be added together, superimposed on a stress state. This whole process is called superposition. So let's write a little bit of that down. Now there are other conditions besides just the material staying linear that have to happen in order for the whole system to stay linear. You could have large deformations and nonlinear behavior that way. In those cases, you can't use superposition. But in our class, we're not going to look at those kind of cases. If you study advanced classes in structural mechanics or structures, then you may find other systems that are nonlinear, what they call geometric nonlinearities. Now when I say the stress states can be superimposed and the stress states can be added together, I don't mean that sigmas and taus can be added together at that particular point. But sigma x's can be added to sigma x's, sigma y's can be added to sigma y's, and tau xy's can be added to tau xy's, and so forth. So this is called superposition. Maybe a new word, but basically all that means is you can lay things on top of each other. Now that's the only theory that we really have for this topic. All the rest is just applying what we already know to slightly new situations. So what we're going to do is work through several examples, and I think after you get through these examples in this lecture, you'll kind of get the hang of it. In this lecture, we'll start off with fairly simple examples. In the following lecture, we'll have more complicated examples of combined loading, and we may be able to work in other things like more circle, finding principal stresses at a point, and different things like that. Alright, so let's start off with this simple example. We have a bar, it's a 2-inch diameter bar, and it has an axial force of 1,000 pounds on it and a torque of 2,000 inch-pounds on it. We want to find the state of stress in this bar, in this material. And I'm going to draw a little square to represent a block, and we want to find the state of stress that's on this block at this position. It's on the side of the bar. If we were to draw the cross-section view, circular cross-section, this point is going to be located here. I'm going to call that point A. So that's this little square right here. So there's some things that you can do to help work these problems, and I encourage a very systematic approach. And the most important thing that we can do is to draw a good free body diagram for these problems. So for a free body diagram, we want to cut the structure at the point of interest. So I'm going to take and I'm going to cut this thing and just a little bit to the left of this point A. I'm going to redraw this structure and I'm going to draw everything to the right of that cut. That includes all the loads that are on it. So there's the 1,000 pound force, and then here's the torque of the 2,000 inch-pounds. Let's go ahead and draw point A on there as well. So it's sitting right there. So if we want, we can make some steps on how to do these problems. I'll leave a little bit of room, but step one would be to draw a free body diagram where the structure is cut at the point of interest. And by the point of interest, I mean that's the place where we want to find the stresses at. Okay, so now we've made the cut. We need to get this thing in equilibrium. In general, we know from statics that we can have 3 forces and 3 moments on a structure. Looking at this, I think it's pretty easy to see without having to go through the summation of forces equations that in order to keep this in equilibrium, we need an equal and opposite axial force of 1,000 pounds this way, and we need an equal and opposite torque. Now, I said 3 forces and 3 moments. Well, the torque is just a moment, but it's about a long axis of a bar. So to keep this in equilibrium, the torque has to come around the backside this way. Okay. The next thing we want to do is we want to look at this particular spot. Let's draw that here. That's the place where we want to calculate the stresses at. And we want to see how each of those reactions contributes to the stress state at that point. Now, I do want to emphasize that we need to look at the reactions. In this case, the reactions are the same as what's applied to the front, but in some cases we can get additional moments or additional torques or whatever at our cut spot that we have to account for from the statics. So it may not directly show up as the applied load, but we would see that as the reaction. So we do need to account for that. So one at a time, let's take them. So we have an axial force here of 1,000 pounds. We notice that the bar is in tension. So the stress that was caused by that is the force divided by the cross-sectional area. So this stress in this direction, we call that the x direction if you want. That would be a value of 1,000 pounds divided by pi over 4 diameter squared. If the force in front was in compression, then the reaction would be compressive, and then these arrows would be pointed inward. The next thing we need to look at then, since we're done with the force, we need to look at the torque. We know that a torque causes a shearing stress, and the formula for the shearing stress from torsion is the torque times the diameter over 2 divided by the polar moment of inertia. Since we're sitting here on the outside, then the radial distance would be the diameter over 2. That's why that shows up in here. The direction that the torque goes determines the direction that the shearing stress will go on that side of the block. So watch this. Let's use a different color. We have this torque coming up the front side, and it's coming around the back side. On the front side where point A is at, that causes a shearing stress that points upward. On the back side, this torque is coming down the front, so that causes a shearing stress that goes down that way. Now we know that shearing stresses at right angles are equal to keep this thing in equilibrium, so we also have shearing stresses that point like this and point like this. So on my block at point A, the shearing stresses will go in these directions: up on the right side, down on the left side, and then these other two arrows to keep it in equilibrium. The value of the shearing stress is going to be the torque, 2,000 inch-pounds, times the diameter over 2 divided by the polar moment of inertia, and that's a formula that I'll give to you on your test. The polar moment of inertia is circular cross-section is pi over 32, diameter to the 4th power. So that would be your state of stress at point A from these loads. Now, a question that I always like to ask on an exam is, after you calculate your state of stress, I'll ask, is your state of stress a principal stress state? Now, a principal stress state is determined by whether or not there's the presence of shearing stresses. If there is no shearing stress, then it is a principal stress state. If there is shearing stress, then it is not a principal stress state. So the answer to this is not a principal stress state. Okay, so that's a real easy 5-point question on an exam. All right, let's take a look at another example. All right, so there's a little bit going on, more going on in this example than the previous one. In this example, we have a bending moment that's applied to the end of our bar, still a 2-inch diameter bar. But there's also a force on the end of this bar, and that would be a shear force I'm going to call V. It's 1,000 pounds. It's pointing downward, and we want to find the state of stress at 2 points, points A and B. They're both 10 inches away from the free end of this bar. Point A is on the top, and point B is on the near side, right in the middle. All right, so following our steps, what we want to do first is to make a free body cut at our points of interest. So I'm just going to cut right here, and I'm going to look to the right of that cut. We could look to the left if we wanted, but if we did that, we would first have to find the reactions at this wall. And I also didn't give the dimension from the wall to the point, so we would need to know that information too. So we're going to look to the right. I'll draw that over here. We have one bending moment that goes kind of left to right on this cross section. That's a 3,000 inch-pound moment. And then the force coming down, that's a 1,000 pound force. Now, to keep this in equilibrium, we have to have an equal and opposite bending moment. Sometimes these can be a little tricky to draw. Sometimes it takes a little experience, but that moment again goes from left to right. If you have one of these click erasers, these click erasers are real nice. You can pull one of those click erasers out, and you can kind of bend your bar left to right to see what's going on. This one's putting the near side in tension and the far side in compression. Okay, so that value of moment is the same as what we're applying to the front. That's 3,000 inch-pounds. To keep this in equilibrium for summation of forces, we need to have a force going up in the back. Right, like that. And that would be 1,000 pounds. However, in addition to that force, the reaction back here will also need to include a bending moment. And that bending moment would be this force distance, this force of 1,000 pounds times this distance for this section of free body diagram. And that bending moment puts the top in tension and the bottom in compression. It's bending it down. Let's call this M2. It's going to be equal to 1,000 times 10 inch-pounds. So let's draw our points on this. Point A is kind of right up here. Point B is on the side. Let's look at a top view of point A, and let's look at a side view of point B. So we're going to go through each of these three reactions one at a time and see how they cause stress at that point. Let's do the moment first. We know that we can calculate the stress from a bending moment by using the formula. The magnitude of the bending stress is equal to the magnitude of m times y over I. This first bending moment, the 3,000 inch-pound bending moment, I said it puts the left side in tension and the far side in compression. So if we look at this cross section, and point B is right here, here's point A. It's bending about this vertical line. So this side over here is in tension, this side over here is in compression. The maximum tension occurs at point B. The stress is in the axial direction, so it goes this way, down the axis of the bar. On the side view, it goes like this. The value of that would be the moment, this one's the 3,000 inch-pound moment, times y, which is half the diameter, divided by the moment of inertia, pi over 64, diameter to the fourth power. Again, the moment of inertia equation is something I'll give to you on a test for a circle and a square and some other basic shapes. At point A, that bending moment does not cause any stress. Point A lies on the neutral axis of bending for the 3,000 inch-pound moment. Another way to think of that is, as far as the moment is concerned, this is the y distance to point B. And we're starting here at the centroid. Since point A lies on this bending axis, the y distance is 0. Another way to think of that is, if I have maximum tension on this side, maximum compression on the right side, right in the middle I don't have any stress. So I do not get any contribution to the stress state at point A for the bending moment. We're done with that one. Now let's look at M2. M2 is caused by the 1,000 pound force being offset by 10 inches. It puts the top in tension and the bottom in compression. So on the top, I get an axial stress. It goes down the axis of the bar this way. And the value of that axial stress will be that bending moment, which is going to be 10,000 inch-pounds times y over I. Now this is a circular cross-section, so the moments of inertia in both directions are the same, pi over 64, diameter to the fourth. If you have a rectangular cross-sections, the moments of inertia are going to be different. We'll do that example later. At point B, which lies on the side, if we sketch in the bending axis, the 10,000 inch-pound bending moment is bending about this line, and that line goes through the centroid. Now the y distance as far as that moment is concerned is going up this time. And point B lies on the bending axis. It has no stress from that moment at point B. Okay, so you can kind of see, imagine how these different bending moments cause stresses in some places and they don't cause stresses in other places. You can think of the bending stress distribution to kind of help us figure this out too. Alright, so we're done with that moment M2. Now let's take a look at this 1,000 pound force. That's a shear force, and the way that we calculate transverse shearing stress in beams is using that force with the formula tau is equal to VQ over IT. These problems really depend on you knowing all the other things that we've talked about as far as stresses go throughout the semester. So if you're not familiar with some of these formulas, go back and refresh yourself. Alright, so let's draw the cross-section again, and let's show this force V on the cross-section. You can look at the front side or the back side, doesn't matter. I'm going to draw the arrow coming down here, and here's point B, and here's point A. Now remember how this VQ over IT formula works. You shade in from the point of interest to the top of the cross-section to calculate your Q area. For point A, we are already at the top of the cross-section, so the Q area is 0. So that means that this transverse shear force does not cause any shearing stress at A. Let's look at point B with that same force. So we shade in from our point of interest to the top of the cross-section. And now our Q area is not 0. The Q is y bar times the area. I will give this to you on a test, but the y bar for a semicircle is 4r over 3 pi. So the shearing stress is going to be equal to that force V times Q, which is y bar times the area. So we have 4r over 3 pi, 1/2 pi r squared. Our diameter was 2 inches, so our radius is 1 inch. We're going to divide that by the moment of inertia of the cross-section, pi over 64, diameter to the 4th power, and the thickness of the cross-section at the point of interest. Now, since point B lies right in the middle, the thickness of this cross-section is going to be this dimension. It's going to be equal to the diameter of the bar. So we'll take and we'll divide that by another 2. The direction that the shearing stress goes at point B is determined by the direction that the shear force goes. So look at this little square right here at point B. The shearing force is coming down on the right side. It's going to cause a shearing stress that goes down on the right side. The reaction force goes up on the left side, so it causes a shearing stress that goes up on the left side of that block. And then to keep this in equilibrium, I have these other 2 arrows. The value of this would be what I have here for tau. Alright, so that's what you do to find the state of stress at point A and B. Now, we can ask the same question. Are any of these a principal stress state? And the answer to that is yes. Point A is a principal stress state because there's no shearing stress. Point B is not a principal stress state because there is shearing stress. Alright, let's take a look at another example. Alright, so this is a pressure vessel. It has a 5,000 pound force on the top of it. It's capped. Now, in reality, you would tend not to use a flat cap on a pressure vessel. I'm just kind of trying to draw this very simply. But this pressure vessel has 200 psi of pressure in it, and the dimensions of the pressure vessel are a 10-inch outside diameter and a 9.8-inch inside diameter. Our point A, where we want to find the stresses at, lie on the outside surface of the pressure vessel. And it really doesn't matter exactly where I show that, so I'm just going to draw that somewhere up and down the side of that. But here's point A right here. So our process still holds. What we want to do is we want to make a free body cut at our point of interest. And our pressure really doesn't come into our equilibrium equations because we accounted for that when we developed our pressure vessel equations. So we have 5,000 pounds on this pressure vessel from the axial force. And there's my point A. So let's draw this point A out here to the side. And if we do our pressure vessel stresses first, then we know that we have a hoop stress from the pressure vessel. The hoop stress is the larger of the two stresses. The hoop stress in a pressure vessel is P times R inside radius divided by the wall thickness. Some books use this as PR over T, but you have to be really careful about what those things mean. R is the inside radius and T is the wall thickness. We've used T to mean something different in VQ over IT. You have to be careful with these symbols. Alright, so in this case it causes an tensile stress in the hoop direction, so that's 200 psi times the inside radius. That would be 9.8 divided by 2 divided by the wall thickness. And in this problem, the wall thickness would be 0.1 inch. We have 0.1 on either side, but what we want is the wall thickness in the pressure vessel equation. In the axial direction, we have tension. And in this case, we're going to have P times the inside radius divided by 2T. But in addition to the tensile stress from the pressure, we're going to have a compressive stress due to the axial force on this pressure vessel. And since I've already drawn this arrow coming out, what I'm going to do is I'm going to subtract away the P over A stress from the axial force. So it's the force in the bar divided by the area of the cross-section, the area of the tube. Now we can use the 2 pi RT if we want. The ring should be small enough to use that way to calculate the area, or we can go and calculate the area of this ring as pi over 4 outside diameter squared minus the inside diameter squared. Okay, both of these would be in psi. So again, we can take a look at the state of stress. This is a principal stress state. Let's keep making these examples a little bit more sophisticated. So in this example, we have a rectangular cross-section bar. It's 4 inches across and 6 inches tall. And it's cantilevered, and it has 3 forces applied to the end, the free end of that cantilevered section. 24,000 pound axial force, and then 2 shear forces on the end. One that goes kind of into the page of 240 pounds, and one that goes up and down of 160 pounds. We want to find the state of stress at 2 points that are located 100 inches away from the free end. Point A is in the middle of the side, and point B is in the middle of the top of the cross-section. So just like we've done before, we want to take a free body diagram cut at our points of interest and figure out the reactions. So let's do that. I'm going to cut this just to the left of these points. I'm going to draw the free body diagram. Let me do that over here. Alright, now I need to include our forces on the front. And now I need to put in our reactions back here on the back side. Now for summation of forces equal to 0, I need 3 equal and opposite forces. So that means that it's coming to the left for the 24,000 pounds. It's going out of the page of 240 pounds. It's going up in the back of 160. But in addition to those forces, I'm also going to get a couple of moments. I'm going to draw the moments in a different color so they're a little bit easier to see. This force of 240 pounds causes a moment that wants to bend this left and right. It's putting the back side in compression and the near side in tension. I'm going to call this moment M1. Okay, that's going to be 240 pounds times 100 inches. And we have another moment from the 160 pound force. It puts the top in tension and the bottom in compression. So it's bending from the top down to the bottom. I'll call that M2, and that'll be 160 times 100 inch-pounds. Now, we don't have a torque on this structure. In our class, we haven't learned how to deal with torsion of non-circular cross-sections. So if you come up with a torque on a rectangular cross-section bar, one of us made a mistake. Either I made a mistake making the test problem, or you've made a mistake doing some of your statics. All right, so now that we have those reactions identified, we want to see how each of those reactions contributes to the stress state at that particular point. Let's do these one at a time this time. So let's first look at point A. So point A is on the side and it's in the middle. So I'm going to label this as a side view of A. Let's do the easy ones first. So we know that the axial force causes an axial stress. It goes down the long direction of the bar, and that's equal to the force divided by the cross-sectional area. So that would be 24,000 pounds divided by 4 times 6 inches. All right. Now let's take a look at the bending moment M2. If you bring in a short ruler to your quiz or something, you can bend it. That ruler would be in tension if you put this kind of force on it in the back at this point A. Tension on the top. Does not cause any stress at point A, however. Let's draw the cross-section and let's see how that is the case. Okay, so point A is right here on the side, and I find it convenient to draw in the bending axis. So it's putting the top in tension and the bottom in compression. It's bending about this line. Point A is on the neutral axis for that bending moment. My over I, that y distance is 0. So M2 does not cause stress at A. Let's just make a note of that. Alright, so we're done with that one. Now let's think about M1. M1 comes from the 240 pound force, and like I said, it's putting the near side in tension and the far side in compression. Let's draw a separate rectangle. There's my point A, and now it's bending about a vertical line. Now the bending stress is My over I, but the y distance depends on your perspective from the moment. In this case, what we would call our y distance for that formula would be this way. It's in tension, so it's going to add to the tensile stress from the P over A term. And the value of that would be the moment M1 times the distance from the centroid of the section, this line, to point A. Now, the whole width is 4 inches, so that distance would be 2 inches. My over I. Okay, now here we have to think about this a little bit carefully. We know that the moment of inertia for a rectangle is 1/12 the base times the height cubed. Or it could be 1/12 the height times the base cubed. Depends on which way we're bending it. The way that I'd like for you to think about it is, if we bend this thing left to right up here, are we bending it in the easy to bend direction, or the hard to bend direction? Well, if you bring your little ruler out and you bend it, it would be very easy to bend that ruler in that direction. It's the easy to bend direction. That corresponds to the low moment of inertia direction for that cross section. So the I term that we would use right here would be 1/12. The base would be 4, and the small dimension, the base would be 6, and the small dimension would be cubed. So now we're done with M1. Okay, we have left to deal with these two transverse shear forces. We talked about that formula already. The formula that we use for transverse shear forces is tau is equal to VQ over IT. Let's draw in the 160-pound force, and let's reuse this picture. So my shear force is coming down this way, and we're going to shade in from our point of interest to the top of the cross-section. Now when I say shade in from the point of interest to the top of the cross-section, that's with respect to the direction that the shear force is pointing in. The shear force will always point to what it thinks is the top of the cross-section. And you can go from the point to the top or the point to the bottom of the cross-section, doesn't matter. So for the 160-pound force, what I would shade in would be the top half of this cross-section. Notice how the shear force goes down on this far side, on the right side. That's going to cause a shearing stress that goes down this way at point A. Even if we just have one of those shearing stress arrows figured out, we can pencil in the rest of them for equilibrium. Now the value of the shearing stress is going to be V, which is 160 pounds, times Q, which is Y bar times the area. Now the entire top is 6 inches, entire cross-section is 6 inches tall, so that makes this dimension 3 inches. So the area is 3 by 4, and the Y bar distance would be 1.5. VQ over IT. Let's do the thickness next. The thickness of the cross-section at the point of interest would be the width of the cross-section. That would be 4 inches. Now the last thing we need is the moment of inertia term. Now here this force goes up and down. When it creates a bending moment, that would be bending about the difficult to bend direction. The moment of inertia term that we would use in this formula for VQ over IT would be 1/12 the base times the height cubed, where the base is 4 inches and the height is 6 inches. It's a little bit tricky. Notice how we have in this term 1/12 6 times 4 cubed. Here we have 1/12 4 times 6 cubed. But the orientation is different. This force would cause a bending moment that would be in the hard to bend direction. In the other case, it causes a force. The force causes a moment that would be in the easy to bend direction. Okay, so be careful with those moment of inertia terms. All right, so that takes care of the 160. The only thing left to deal with is the 240. And on the front side, the 240 goes this way. And to calculate the shearing stress at point A, we would shade in from the point of interest to the top of the cross-section. Now this 240-pound force thinks that this edge is the top of the cross-section. So when we shade in from that point to the top, there is no Q area. So we have no shearing stress contribution at point A for the 240-pound force. All right, so we can calculate these terms. And this point A is not a principal stress state. We'll get a new page and we'll do point B. Okay, so I wanted point A to stay on this page, so I just made it a little bit smaller. Now we're going to do the same sort of analysis at point B. And what I might suggest is you go ahead and pause this video and see if you can come up with the state of stress at point B before we talk about it together. Alright, so let's look at point B. It's sitting at the middle of the top. So now I'm going to take a look at a top view of point B. we're going to go through each of these reactions and see how they contribute to the state of stress at point B. Alright, now we have the axial force. Every point on that cross-section is in tension from that axial force. I'm going to cross through that to make sure that we've done that for point B. That's going to cause a stress just like at point A. That's just 24,000 pounds divided by the area of the cross-section. Alright, let's look at M2. M2 puts the top in tension and the bottom in compression. Point B is on the top. So we're going to add to this the 160 times 100 times the distance from the centroid of the cross-section to point B, which in this case is going to be 3 inches. Now this is the difficult to bend direction, so we're going to use the high moment of inertia. It's 1/12 the base times the height cubed for that cross-section. So we're done with M2. M1 puts the near side in tension and the far side in compression. It is bending about an axis that goes vertically. The y distance for point B is equal to 0. M1 does not cause any stress at point B. So we're done with that one. Now let's take a look at our transverse shearing forces. The 160-pound force comes down this way. There's point B. We shade in from the point of interest to the top of the cross-section. Well, there is no area, so we have no shear stress contribution from the 160-pound force at point B, so we're done with that. But we ought to take a look at the 240-pound force. There's point B. Now, same deal, tau is equal to VQ over IT. The Q area is determined by shading in the point of interest to the top of the cross-section. Now, as far as this force is concerned, you see how this force goes left and right. It thinks that the side over here, or this side over here, it doesn't matter which one, it thinks that this edge or this edge is the top of the cross-section. So when I shade in from the point of interest to the top of the cross-section, I have to shade in the entire half of this block. That will cause a shearing stress at point B on the top that goes in this direction because that shearing force goes that way. So on this picture, since we're looking at the top, it would go in this direction. I just need one of those to pencil in the rest for equilibrium. I do want to see your stress blocks in equilibrium, so please go ahead and draw all the necessary arrows in there. But the value of the shearing stress would be V, which is the shear force, times the Q, which is y bar times A of what I just shaded in. Now the entire cross-section width is 4 inches, so the distance over here to the edge would be 2 inches, so that means the distance from the centroid of the cross-section to the centroid of the shaded area would be 1 inch. So that's the y bar. Now the area would be, this time, 2 by 6 inches. This is the easy to bend direction. If this 240-pound force causes a bending moment, that would be bending about the easy to bend direction. So another way to think of that is that it thinks that this edge perpendicular to the force is the base dimension. So the I would be 1/12 the base times the height cubed. And the thickness of the cross-section is the last term that we need. The thickness of the cross-section is the same, it's parallel to the base dimension. In this case, it's going to be 6 inches. Right. So here we have the state of stress at point A and the state of stress at point B. Neither one of these are principal stress states, but take a look at them, see what terms are in common, see what terms are different, and like I said, pay particular attention to the moment of inertia terms. Okay, I think that's good enough for this lecture. When I get the next lecture prepared, it will have similar examples to this, but with little sophistications thrown in.